Good morning, good afternoon, wherever you're calling in from. My name is 𝗏𝗏𝗧𝗏, and I'm the engagement lead here at the European Biochar Industry Consortium, EBI, and we're the industry representative for biochar in Europe. And very excited today to be hosting Dr. Marie-Liesse Aubertin of IFP Energies nouvelles and presenting her latest publications and findings around the Rock-Eval thermal analysis with regards to biochar, quantifying biochar in arable soils. Also, we have Dr. Anna-Lena here to help me with moderation and driving discussion and questions. And she, of course, comes from Carbon Future and as well sits on our board. So as you see right now, we have cameras and mics turned off for all participants. That's only so that we have a smooth presentation and a set stage for Dr. Aubertin. Later, we'll allow for the discussions and questions part. We'll allow folks to turn their mics and cameras on, shortly introduce themselves or quickly introduce themselves, and be able to interact a little bit more intimately one-on-one. If you have questions in the meantime, please feel free to use the chat Q&A, as well as, let us know where you're calling in from, as well as you could feel free to introduce yourself in the chat. This session is being recorded, and we will use this as a resource on our YouTube channel in the coming months. Likely in the new year, we'll get this up. So hopefully a helpful resource moving forward beyond today. So without further ado, I'll pass it on to Anna, maybe to introduce the topic a little bit more and in kind of the big picture of biochar and the importance of Marie-Liesse's work. So Anna, please.
Thank you. Great to see such a big audience of interested people here in biochar persistent and how we can measure it. Maybe briefly for myself, my background is in materials chemistry. My PhD is in inorganic chemistry, so I did a lot of analytics and synthesis in the field of inorganic chemicals, and then worked a bit more on energy exchange materials in PV and in batteries. So I might still have some ideas about quantifying and analyzing chemical materials and their reactivity in different conditions, and that's useful for what we're doing here, because we can remember that the idea of durable carbon removal and biochar carbon removal as being one of those techniques that is already really widely applicable globally is always to get that gaseous form, get that CO2, transform it into something that is less likely to be re-emitted in the form of a greenhouse gas, so either CO2 or methane, and tackle, sequester, hold it somewhere where the risk of re-emission is small. And that's really depending on the chemical form of what it is, the bonds, the strength, the thermodynamics and the kinetics of how it could then react into something else again, and also the position in the environment and the stresses it's exposed to. So we're focusing on soil, and that's really for now the most important application type to store biochar. And it's super important for us as a global society right now to understand what the climate service of sequestering this biochar is. We're often talking about the use case of balancing fossil emissions, and something that is in the atmosphere forever should ideally be only offset by something that is not in the atmosphere forever. And hence we have, I think it's over 8 biochar carbon removal methodologies that quantify the persistence and the effect of this activity. And they're all updated this year, and they're all looking for more insights from science on how to do it. So I'm super excited to hear this approach of Rock-Eval and understand what we can learn from it. Thanks.
So without further ado, Marie-Liesse, if you have access, please share your screen. And
yes. Okay, it should work. Is it okay for you?
Yeah, perfect.
Yeah, great. So I'm Marie-Liesse Aubertin, and I'm working at IFP Energies nouvelles in the Parisian area in France. And I'm a research engineer there, working especially on soil science, and especially on carbon sequestration in soil using biochar. So today I will have a presentation in two parts. So the first one is about biochar persistence. And the second one, I will go a bit more into detail on a technique to quantify biochar using, that's a technique that we developed at IFPEN based on the Rock-Eval thermal method. So before that, I will, make a brief reminding about what is biochar. So biochar is produced from organic biomass. So it can be of all kinds of biomass. And this biomass is pyrolyzed. So it's the increase of temperature without oxygen. And during the pyrolysis, there are some emissions of gas and oil that can be reused as energy. And the solid residue of the pyrolysis is what we call a biochar. It's a charcoal, so enriched with carbon. And what we really call biochar is the charcoal which is produced in the intention to increase carbon sequestration in soil. And moreover, it can have positive or maybe sometimes negative. It's something we can maybe discuss later about the biomass production. And then the biomass can be reused and pyrolyzed. Yeah. So why do we care about biochar? It's when we speak about biochar, we often present the 𝗕𝗏, which is a specific soil type of soil that we discovered some years ago. I think it was in the 80s or maybe a bit earlier, which is located in South America and especially in past human settlements dating from the pre-Columbian period, so a very long time ago. And this 𝗕𝗏 is very specific because it is much darker than the surrounding soil, as you can see on the picture. And it's enriched with charcoal. This charcoal originates very probably from past human activities. And so the discovery of the 𝗕𝗏 showed us two things, that the charcoal and also the biochar can have a positive effects in the increase of in the yields of the cultivations, as you can see on the pictures. And the second thing that the charcoal can remain in soil for a very long time period. So we start with the first part of my presentation, biochar persistence in soil. So we will really focus on this aspect of biochar amendment. So during my PhD, I made incubation with soil inoculum, and I compared biochar with more fresh residue. So it was with compost. And so here we can see that. So just to present, here we see the cumulative CO2 emissions during the incubation. So the higher the CO2 emitted, the better or the more the material is decomposed. And here you see that the compost, which is not pyrolyzed, decompose much faster than the biochar. And you see that the biochar even doesn't degrade at all. So this was only one study, but if you look to a lot of other studies for also different experimental duration, you see that they all find the same thing, that, well, okay, maybe at the beginning, biochar can decrease, decompose a bit, but then it really it doesn't decompose anymore. As you can see here, biochar remaining in soil remains very high even after 8 years. So if we again compare with compost, you see that biochar doesn't decompose even after maybe 100 years, and the compost decomposes much faster. And then there are a lot of different models existing to try to find the mean residence time of biochar. So how long can biochar remain in soil? And the review from Wang et al. Found that the recalcitrant pool of carbon can remain more than 500 years. And they also found that biochar is composed of both labile and recalcitrant pools of carbon. And the recalcitrant pool of carbon, which remains in soil for a long time, is much larger than the labile pool. And so the first so the higher degradation that you can see on the left with the small experimental duration are due to the degradation of the labile pool, and then remains only the recalcitrant pool who stay for a very long time in soil. For this reason, recently the IPCC proposed the biochar as one of the carbon dioxide removal methods. And so it's presented as a possibility to take indirectly carbon from the atmosphere and then to store it for a long time period in the land, in the soil. So now, so there is not one, but a lot of kind of biochar depending on their initial feedstock, so on their initial biomass, but also on the condition of their pyrolysis. So here are some examples of different feedstock, so wood, sewage sludge, straw, and manure, and you see that they induce different contents of carbon fraction, with the wood having the highest organic carbon fraction there in the biochar. And here are some examples of different comparison from pyrolysis condition. So especially the temperature of pyrolysis and the time of pyrolysis. And so the higher the temperature, the higher the half-life, so mean residence time of biochar. And the same for the time. The longer the biomass is pyrolyzed, the more stable or biologically stable is the biochar. So this can be explained also chemically, because the more we increase the temperature, the more aromatization and then condensation occur during the process. And also the biomass condenses the carbon, and so it has a higher content of carbon during the pyrolysis. But so I spoke here about the internal factors explaining the persistence of biochar, but there are a lot of other factors, especially when the biochar is amended on soil. Then the type of soil, its clay contents, mineral contents, texture, also have a very strong impact on the persistence of biochar in soil. The climate as well, because in cold climate, the biochar will be even more persistent. Yeah, and of course, the biotic parameters, so the amount of fungi, bacteria have an impact on the persistence of biochar. So when we amend biochar in soil, then the question is where in which part of the soil does the the biochar remain. So here is an example of a field study which lasted 9 years, and they compared so controls a soil without biochar and a soil with more or less biochar, so in purple and in red, and they saw that the biochar is found after 9 years. The biochar is stored in the stored with mineral associations, so it's stored on clay and minerals, and only a small part is located as a free particulate organic matter. But actually, the free particulate organic matter is more enriched than the particles which are occluded or associated with organic matter, with minerals. And so finally, the free particulate organic matter contributes a lot in the enrichment of carbon in the soil due to biochar amendment. But this free particulate organic matter is very mobile in the environment. It can be transported horizontally through erosion, rainflash, flow, or vertically through different processes, so more infiltration, bioturbation, leaching, colloidal transport, and at the end it deposits somewhere else in the environment. So it can be in the soil or in the ocean, in the river flows. If we look now in the field, agricultural field, we see that once the biochar is applied, so or it remains in the field, or it's transported, for example, in a river, and therefore it's interesting to quantify biochar in this field because it allows monitoring the carbon stocks in the field itself. So to ensure about the spatial homogenization, to monitor through time the carbon stock evolution. But it's also interesting to monitor the deposition areas of biochar. And the quantification also allow monitoring the effect, to understand the effect of biochar soil ratio on the agricultural properties, because it's always important to look at the agricultural properties when we amend with biochar. So now we move on to the second part of my presentation, which is so a bit more into detail, a bit more technique about the quantification, and it's the results of what we published in August in this paper. So in general, to quantify biochar soil is not that easy. Different methods exist. So there are, say, 4 big types of methods: chemical, thermal, 𝗵𝗶_𝗃, which is a molecular marker, and optical method. So when we compare this method, we see that they do not focus on all the types of pyrogenic organic matter. And for example, the chemical method do not cover the whole range of biochars. There is also a limitation for the indirect method. So chemical method and 𝗵𝗶_𝗃 are not direct, so it needs pretreatment. It's a bit time consuming. Yeah, and optical method, it's also very time consuming, manipulator dependent, and with the optical method, you don't see the very small particles. So it has all these methods have limitations. But the thermal method, recently a paper from Hardy showed that with the thermal method, we can it can help to quantify biochar in soil. And and so they work with differential scanning calorimetry. And they show that, so this method is let's say, practical because it's more direct. You don't need any pretreatment, so you just need to dry your sample to ball mill it, and then you can measure. And they saw that the biochar has a very specific thermal signature. So here you have example in green soils without a lot of biochar in it, so mostly minerals or uncharred material. And in black, or the peak, the more on the right, is soil plus a lot of biochar. And so they say that it's possible to quantify biochar in soil, but the only thing is that there is some recovery between those peaks, and the recovery makes it more difficult to have precise quantification of biochar. So at IFPEN, we developed so the method, thermal method of the Rock-Eval. And if you compare Rock-Eval with 𝗕sci, you see that the Rock-Eval has also another stage, which is the pyrolysis, because the 𝗕sci is only oxidation, and then basically you measure the heat that is involved by the oxidation. While the Rock-Eval, you have first a pyrolysis stage, and then an oxidation stage. And during both stages, you measure carbon through hydrocarbons, CO and CO2. And so we made the hypothesis that maybe the Rock-Eval allow a greater precision of carbon measurement, and so may reduce maybe the carbon recovery between charred and uncharred organic matter. And so maybe that at the end we have a more precise estimation of biochar quantity. So we tried making a mixture. So we made mixture with 6 different biochar on 4 soils from cultivated fields. So the biochar were made industrially with different type of biomass, and the soils had also some difference in the content of organic carbon and mineral carbon, and the texture was also different. And then all those mixture were so mixed with different ratios, going from 0, it was pure soil, and up to 1% of massic biochar in the soil. And then everything was measured with the Rock-Eval, so the biochar alone, the soil alone, and their mixture were all analyzed. So yeah, this I already explained, but it's just to say that so here I just explain a bit more into detail what is the Rock-Eval. So as I explained before, we measure carbon, and yeah, it's important to say that it's continuous measurement during the temperature gradient. And so at the end we have thermograms, so it's emission through time and through temperature. And based on this thermogram, we can measure standard parameters. So total organic carbon, mineral carbon, for example. And so if we look at the results from the biochar soil mixtures, so here are the 5 thermograms so that I present. So this, what you see on the left, here are the results with this with our samples. And we see that, so here is an example of one of the mixtures with all the different ratios, but it was basically the same for all the mixture. And we see that during the pyrolysis, we don't have an evident effect of the increase of biochar in the soil, whereas during the oxidation, we could see very well that there is one peak which was bigger with the higher ratios. And more especially the CO2 emitted during the oxidation stage represents most of the carbon emissions during the whole analysis of the Rock-Eval. So for the quantification, we were based on this type of emission, CO2 during the oxidation. So here was only one mixture with different ratio, and when we see all the mixture with all the ratio, we have that. So it's on this CO2 from all the mixture, and we see that they all behave the same. Just this peak is something else. It's inorganic biochar. Inorganic carbon. But otherwise, they all have a peak due to the presence of biochar. And when we want to compare all of them, we measure the variance for each mixture using all the ratios. And so it gives this. And we could evidence that all the peaks due to the presence of biochar were all located between 410 grades and 610 degrees. So yeah, to explain, so this mixtures is only this line. And so based on this, just for the ratio with 0, it's the soil alone, and the soil also emits CO2 during the oxidation at this range of temperature. And so how can we explain these emissions? It's because this peak is due to biochar, to the presence of biochar, but also to other kind of molecules. So it can be also charred organic carbon, for example, due to natural forest fire. But it can also be due to the presence of uncharred organic matter, which is very recalcitrant, like, for example, lignin. So fresh lignin would also would also emit a peak at this place. So to quantify biochar in the soil, we measure the area of this peak, and we removed the reference, so the pure soil. So what we call the reference sample is really the sample with the lowest emission of CO2 emission between 410 and 610 degrees. So the best is when we have a pure soil sample without any biochar, but in some case we don't have pure soil, so we take the soil with the lowest biochar compost, so with the lowest peak, and so it gives at the end the relative quantification. In our study, we had a pure soil, so we used it, and it gave a very good estimation of carbon content. Then, so here in this line, we have all the mixtures and all the ratios, and we saw that independently on the ratios and the mixture and on the soil, we have always very good estimation. Then we applied it on a real case. So it's an archaeological soil, 𝗕𝗏, and we compared our method with another method which is widely used, which is the VPCA. And we saw that the relative quantification was good, so comparable to the VPCA method. So we had a good estimation also for the archaeological soil, for this archaeological soil. And so now I move on to the conclusion. So we saw that biochar is persistent in soil. It can remain in soil for a very long time period. I described the methodology based on Rock-Eval to quantify method. We saw that we have a good estimation, but we still have some remaining questions. So we are not sure yet about how when a biochar is weathered, when it's aged, what is the impact on the thermal signature? Does it change a lot? we think that no, but we didn't prove it yet. And then, so our method work very well with soil from cultivated fields, because those fields are mostly not very enriched with carbon, organic carbon. But maybe that our method will be a bit more difficult with soils with a lot of carbon, like forest soils. So maybe we can improve again our method. And it can be a bit tricky when we want to compare different soils having different reference. Because if we don't have per soil, we have to use a reference for each type of field. And then the comparison between different fields can be a bit difficult due to the use of maybe different reference samples. And so yeah, so I spoke today a lot about carbon persistent in soil due to biochar addition, but it's very important to also look on the other effects of biochar, because it will remain for a long time in soil. So we also have to look on the side effects. We know that in the tropical soils, it mostly have beneficial effect on the agricultural parameters. But there is today no consensus about the beneficial effect of biochar in the thermal areas, in the fields of the thermal areas. So we have to keep that in mind when we put biochar in. And maybe there are also other effects in the environment. So this is an open question. we also have to think about it. Yeah, because once the biochar is in soil, we cannot remove it anymore. So we have to be sure of what we do when we put biochar in soil. And with that, I'm finished. Thank you for your attention.
Thank you very much, Marie-Liesse. Very insightful and very interesting. I know, folks, that we don't have any questions in the chat, but I'm sure that there are many thoughts to be shared. Anna, I don't know if you want to take over just for a minute while I allow folks to raise their hands as well as access their mics and cameras. So if you do have a question, yeah, I'll ask that you raise your hand, and then we'll eventually get to you, call your name, ask you to introduce yourself, and we can allow you to ask your question and drive discussion.
Wonderful. Yeah, I see the first one already. I would love to also understand what this little R registered trademark in Rock-Eval is. Maybe you can dive a bit deeper on the history of how this method came into place. and
yes,
who receives money for when you do it, or how does that work?
Okay, so why it was created and all, the story of the method?
Yes, yeah, so and why is this registered trademark? I mean, that's unusual to see it in the headlines of a scientific paper a bit.
Yeah, but it's an interesting story actually, the Rock-Eval, because it was created by IFPEN for the petroleum purpose. So the idea was to explore a new place where we can get petrol, to have an idea of the maturity of the rock. For the petroleum exploration. Initially, it was built for that, but about 20 years ago, we discovered that it was also possible to use it to characterize organic matter in the soil. And so now more and more research is made using the Rock-Eval. Yeah. And who produced it? So it's 𝗲𝗀 technology. So it was created by IFP Energies nouvelles, but it's put on the market by 𝗲𝗀 Technology, which is another company. Yeah. Does it reply your question? Or?
Yes, that's great. And it's just important that people use the little R if they're mentioning it, but it's not in a way limited in use, or do you need, if you want to use it, do you need kind of get the license and the authorization from someone?
I don't think so, no.
Oh, yeah, okay. Right, now we have plenty of questions. So let's see. maybe, so if that now works, that you can come off mute. Thomas Harcourt, you had the first one about how biochar and lignin can be differentiated in soil. Would you like to, that's a clear question. You can also come off mute and add something. Thanks.
No, yeah, I was just looking at the curves and like you said, Marie-Liesse, that there was an extra peak where lignin was being detected, and I was wondering how can that be differentiated, and are there any other aromatic compounds which could influence the result? Thank you.
Well, this is I think the difficult part in this method is that it's not that easy to distinguish because the peak is at the same place. So yeah, I think we cannot easily distinguish both peaks for now, okay. But so it's something that we have to improve in the method.
It's maybe complementary, where you would need another methodology, another analysis tool that can quantify the nature of the organic carbon fragments. Ahmed, please.
Oh, hi, can you hear me?
Yes.
Yes.
Okay, thank you for the presentation, and thank you guys for arranging this. That was fascinating. I have a question because you probably don't know that we've done already 300 Rock-Eval method. We use the Hawk machine, so our papers all have the Rock-Eval technique in there. And there are a few things that I'd like to get your comments on that. The first thing is the peak above 600, which you call it S5 peak, and you refer to it as a mineral carbon. Those are actually biochar. It's very simple. You could actually compare the LICO total carbon and total organic carbon with the Rock-Eval, and you would see huge discrepancy. And that's because the mineral carbon S5 is in fact a fraction of biochar. Biochar is so carbonized that is even more resistant than mineral carbon thermally. That way it takes more temperature than dolomite and calcite. So that's one common question I'd like to hear, because if you could see even your soil, just the soil control data, you had no S5, but then in the biochar peak you had a huge S5 peak that it doesn't even come doesn't get completed at 800 degrees. So it's quite a lot of biochar in that peak. The second question I have is so you're basically focusing on the S4 peak, which is oxidation peak. And a lot of biochars, especially biochars that are produced at a lower temperature, they have substantial amount of S1, S2, S3, you name it. And those are actually more important for biochars because those are the non-persistent fraction of biochar. So, just assuming that only S4 is determinant of biochar, you're missing the big picture of the biochar. So that's why, we're recommending combined methods, 2 or 3 different methods, which we explained in our paper, in the inertinite paper, that kind of use a different approach to bring the full picture. So yeah, that's it. I wonder if you have any comments on this.
Okay. So yeah, so I start with the first question, the S5 peak. So I show it again. Yes, here you were speaking about this peak above 610. Yeah. So here we are sure that it's minerals because even the pure soil has it, because we used 4 different soils. And in this specific soil, we had a lot of minerals, so we know about it. And so you said that in some cases the biochar may be emitted there, maybe if the biochar has been for the gasification. So if the pyrolysis went up to more than 1000 degrees, so very high temperature, maybe that we have a peak there. We didn't try actually because on the market most biochar are produced around 400, 600 degrees. So it's a very specific condition, I would say. And it takes a lot of energy to produce biochar with so high degrees. And also with the gasification process, the yield of biochar is always very low. So there is no benefit to make biochar in this temperature. So it costs a lot of energy, and at the end you don't have a lot of biochar. So most people don't produce biochar in this temperature. So this was for the. Sorry.
I was wondering if you have a picture of the Rock-Eval analysis of the pure biochar in the slide deck.
Of the pure biochar, I don't have it on this slide. Sorry.
Okay.
Yeah, sorry, I should have put it maybe, but yeah, it would be only a peak alone, maybe much higher.
And nothing around 600 then?
No, nothing.
Oh, interesting.
Not with
and that is in contrast to what Hamed you're observing, or is it depending on the type of biochar?
It depends on the type of biochar, because the biochar that we used were produced between 400 and 650. Yeah. So it's not the same type of biochar than what was said in the question. Yeah, so that was for the first question, and the second question was about the S4 peak. So basically this peak, and you said that some biochar also emit peaks at other for other emissions. So it could be the case, but I think it's only for the biochar which are produced with very low temperature. So lower than 400 or even lower than 300, I think. So yeah, I don't remember. I think we didn't try with biochar with lower temperature than 200, but we know that the method works when the biochar are produced between 300 and I would say 800 or something like that. But yeah, I think most of the biochar which are produced are really produced around 500 to 600.
Interesting. So maybe Hamed, you'd like to come back. I hear different questions, and you have a follow-up also. Like, should we model more than one peak? Do we need to know what biochar we're looking for in order to build an analysis routine on fitting these curves? Whether it's all the peaks or just one, and if it's just the one, why don't we just determine the fixed carbon? If you'd like to comment again.
Okay, here Henrik Petersen. I'm sitting together with Hamed.
Nice.
Just a comment. I mean, we have just quantified the carbon fractions in the number of biochars ranging from 500 up to 800 degrees, and there's definitely degradable organic carbon in biochars below 550 degrees. So you cannot ignore these peaks. It's definitely there. We can quantify the quantity of degradable organic carbon. And we also know that we don't need to go to 1,000 degrees. We have a lot of biochars up to 850. And above 600, 650, they are basically all similar, because you have a carbon-rich, polycondensed aromatic structure. And then you can't talk about different biochars. It's all the same. And that's the whole point how we have been doing here the last couple of years. And that's by comparison to ecology and nature. Just a comment.
Okay. No, very interesting. I'm not sure to hear you very well. So what I understood is that so you work with biochar produced at temperature higher than 600, and that you can see a peak above 610 degrees that you said. Yeah.
Well, we work with a lot of biochars produced from manufacturers both around Europe and here in Denmark. And they all provide production temperatures, and that's another issue. You need to convert the production temperature to actual carbonization temperature, which is the temperature the biomass has been subjected to in the oven. And that might not, definitely, very often not be the same as the production temperature.
I'm not sure to understand the question because I don't hear it very well actually.
So what I understood is that you need to do a transfer of not just the temperature that producers set their machine to, but really look at the conversion temperature that the biochar or the biomass material has experienced in the furnace or in the chamber, and that could be different.
Okay,
but it sounded like they've used a range of biochars, and it sounded like they're seeing the peaks.
Okay, but that's interesting because
maybe
we
you can
didn't see
follow up on that.
I would be interested to see which biochar you used. Was it pure biochar? But very interesting because for now we didn't see it ourselves, but maybe some biochar, I don't know, have it.
Yeah, interesting. So let's see. Then we have a question from Jenny K. What is the advantage or disadvantage of this method versus the others? So, for example, and you say method of probably determining biochar persistence. So for that, we've used proxies like C/H ratio, or we're using random reflectance. Hydrogen index could be one that's established. Hydrogen pyrolysis. Would you like to speak about that?
So comparing with C/H ratio, okay, but I partly talk about it there. So the advantage of the Rock-Eval method is that it's a direct method. It takes lower time than the method which require pre-treatment, like chemical method and molecular markers. They need oxidation pre-treatment, and it can take some hours at least. But with the thermal method, it's very rapid. So it's the first advantage. And also the optical method is very time consuming. And so I think this is the main advantage. And compared to the DSC, so the other advantage is that it's again more direct than the DSC because the DSC measures the heat while we measure the carbon. It's even more direct because for the heat we need a conversion factor. Yeah, I think this is the most advantage. And with the Rock-Eval, you can also measure a lot of other things. Actually, you can measure directly the total organic carbon, total mineral carbon. So with one analysis, you measure a lot of things. So I think this is the most interesting thing. And for the disadvantage of the Rock-Eval method is that we also have a bit of carbon recovery. So the precision is not 100%. And as we said also before, for now we can hardly identify or differentiate between biochar and lignin. This is, I think, the biggest limit. But I think it's the same limit than for all the thermal method. Yeah.
Excellent, thanks. Jenny, would you like to add something? Is that well answered?
No, thank you. That's a good overview.
Great. While we're at it, I'd love to hear, you said it's quicker, but just thinking of a world in which biochar producers send in their samples regularly for inspection, would you also recommend it for looking at the biochar itself as a material, or would you recommend it really rather for something to look at biochar in soil if someone thinks that just documenting the introduction of biochar into soil is not enough and we need some additional monitoring? Which use case do you think is most relevant here?
I think you can use it for both. So for biochar per soil, as we saw, it's possible, but we also use it for pure biochar, and also it gives some more information about the biochar itself. It can give information about the temperature of pyrolysis, the maximum temperature of pyrolysis. So, for example, we can see it, yeah, especially on the hydrocarbon emissions. So if the biochar is produced in very high, okay, let's say at 500 temperature 500 degrees, you will see a peak. If you put the biochar alone, pure biochar for analysis, you will see a peak starting a bit here after 500, and you won't see any parallelized emissions before 500 because the biochar was already parallelized up to 500. So it gives you an indicator, an estimation of the maximal temperature of pyrolysis.
And do you have fees for this analysis? Is that available on your website? I haven't checked, but that could be a question that people have. How much does it cost? What are the waiting times? Like, you don't have to say them right now, but that could be something.
I'm sorry, I don't have the answer for the for this.
Okay, great. So let's see. Ahmed, I've seen your hand. I'll get to that in a bit. I just wanted to also hear Maria. You had a question. Would you like to come off mute and ask it yourself? It's about DSC and TGA curves and how that compares. Are you here? Otherwise, let's see. So I'm Maria Fernanda.
Yes.
Hello,
yes,
hello. There you are. Welcome.
Yeah, actually, I know a question. It's just a comment to complete the Marie-Liesse talk.
Okay.
So you can read it. So,
all right.
Yeah.
Excellent. Thank you. So then, Hamid, would you like to join again?
Yes, I have a quick question. If the soil has a large quantity of residual carbon or S4, I mean, soil is highly degraded and already had some wildfire or something like that, and you have no access to the pure soil control samples, is there a way to, I mean, then later you add biochar in it, is there a way to separate biochar from the soil with the already high residual carbon? Or you have to know the control before subtracting and getting the result?
Well, this is one of the limitations of our method, is especially this, because as we saw before, it's difficult. We have the same peak if it's a biochar, or if it's pyrolyzed carbon from a forest fire, or if it's lignin. So this is a bit complicated to differentiate between the content of all those materials. So in the case you proposed, we can only measure the relative addition of biochar. In that case, it means that we need to have a sample of the soil before biochar amendments and after. So only what we can do with this configuration.
Maybe you can try to do it like 𝗕𝗏𝗀𝗃 to pick out the biochar from the soil sample.
Yeah, in that case,
probably
yeah,
not
it's
ideal.
possible.
Yeah. So we have a question from Johan Lombard, and I think we've covered that. It's about quantification of biochar produced via gasification, so 750 and above. So yeah, we've covered that, I think. Talked about it. There might be another peak above 600 coming in, and it's also possible to do that. If not, please add on your question. And then we have Richard Johnston saying that as we assume that manufactured biochar is composed of a labile and more recalcitrant biochar, is this method more for the more recalcitrant biochar, for the more inert one, or is it also valid to quantify biochar that has more of the labile fraction?
It's valid for both biochar, but the quantification is mostly based on the recalcitrant part. But generally in biochar, the recalcitrant part, it's much more than the label. The label is really well, again, it depends on the biochar, but it's only a few % of carbon generally. Then it depends if you mix biochar with something else, of course, then it changes. But yeah, I would say if it's a biochar with not a lot of label parts, then our methodology works well. But if you have a lot of label part, then you have less precise results, I would say.
I see. Okay, thank you. So cost and ease. We have a question from Michael Ozulu, whether Rock-Eval could be suitable and mature enough to use in soil organic carbon projects to quantify carbon farming carbon sequestration.
Yes, but it's already used in projects with soil. It's widely used already to characterize organic matter in soil, and it has been proven that it estimates very well in general the organic carbon in soil.
But then we would again be faced with the question of how durable is the carbon that's in the soil? Because if we cannot say if it's lignin, then or inertinite biochar, semi-inertinite biochar, if that's difficult to differentiate, then putting a estimation of the persistence might be a challenge, or maybe it's solved.
Okay, what the Rock-Eval gives is that it gives the thermal characteristic of a soil, and generally we assume that the higher, if the emissions are emitted at low temperatures, generally it means that carbon that you can then quantify is more labile. And if the emission is emitted at higher temperature, this carbon is more stable. So you can compare soils, the stability of soils with this information.
Yeah, I think that's very useful. Thank you for taking your time and explaining it. I'm seeing that we're reaching the hour. So Troy would like to finish and close us here.
Yes, thank you very, very much, Marie-Liesse. Very insightful, very practical, and thank you for taking the time as well to answer the greater questions and discussion. And thank you, of course, Anna, for driving discussion and helping filter here between the audience and Marie-Liesse. Very well done. So as mentioned, we're at time now. This webinar will be up on our YouTube channel, so if you ever want to use it as a resource, we'll have it up there in the coming weeks. As of right now, we don't have any planned webinars coming up, but again, really want to thank Marie-Liesse for your time and expertise and insights. Very happy to host you and give you this platform. So thank you very much.
And thank you for your invitation.
Great. Hope everyone enjoyed and found this as insightful as I did, and hope everyone has a great rest of their day. So thank you and take care.